This is the 25th lecture of the course MTH 204A for section B. Recall that in the previous lecture we were talking about ideals of rings. As I have already told there that ideals are the analogues of normal subgroup in the setup of rings, and in the normal subgroup we have already seen that they are intimately connected with homomorphisms. So, the same we are going to see here as well. So, the ideals will be independently connected to ring homomorphisms. So, first let me define what a ring homomorphism is. Let R and R prime be two rings. I would like to remind you that for us a ring means always it is a ring with identity, and a map from R to R prime is said to be a ring homomorphism, said to be a ring homomorphism if, of course. So, what do you mean by homomorphisms in general? They are the structure preserving maps. So, in rings what are the structures? Structures are given by the operations addition and multiplication. So, by a ring homomorphism I mean the maps which preserves for every A, B in R, and in this case we do impose a further condition that phi of 1 should be 1. Let me say a few words about this. So, this shows that phi is a homomorphism between the from the additive group of R to the additive group of R prime, right. So, that ensures that the additive identity, that namely the 0th element goes to the 0th element there, but alone these two conditions do not imply that the one will the multiplicative identity name which we call as the unity goes to unity, that is not guaranteed. So, we impose this condition further. So, thus for us by a ring homomorphism we mean a structure preserving map that sends unity to unity. Okay. Let me give you some examples. Okay. So, the first example is let us take the most obvious one, identity, okay, or in general suppose that we are given two rings R and R prime. So, then from R to R prime the map sending each x to itself. So, this is a ring homomorphism, the inclusion map. Okay. Okay, I should say one more thing that in case of groups we do have trivial homomorphism, namely which is sending each and every element of the group to the identity of the other group. But in case of rings, unless R prime is the trivial ring, that is the ring with only one element, namely the 0, unless R is like that, certainly we cannot have any anything called trivial homomorphism, because 1 has to be mapped to 1. Okay. So, we do not have anything like that unless the very isolated case that R prime is trivial. Okay. So, the next example that we are going to talk about is a quite common map which we have already seen, namely this reduction modulo n, that is we send each m to m plus nz for every m. It is easy to see that this is also a ring homomorphism. Okay. Third, so in fact this is an interesting observation. Given any ring R, there exists a unique homomorphism, let us say phi from Z to R. Okay. Why so? Because let us try to see whether, let us first try to find out a homomorphism from Z to R. So, if phi is a homomorphism from Z to R, then phi of 1 should be 1. So, what do we obtain there? Phi of 1 must be 1, then what should be phi of 2? It must be adding the unity of r prime unity of r twice. So, by induction phi of n should be okay, and similarly when n is, so this is for every positive integer n, and then of course you must have phi of n when n is negative is certainly phi of minus n, okay, for n negative. Okay. So, I mean it shows that I mean this in fact shows that the homomorphism is unique, because like again let me repeat that sending each positive integer n to the sum of n times sum of the unit itself for n times, and for negative integers by defining like this we can immediately see that it is a homomorphism, right. It is trivial to see, and also this analysis shows in view of this property that if phi is a homomorphism from Z to R, then phi must be like this. So, we have checked both the ways. So, again let me repeat that if we define phi like this, that phi of n is this and phi of n is this when n is negative, then it is easy to see that it is a homomorphism. And at the same time, and on the other hand, in view of this property we really verified that any homomorphism must send n to this and positive integers to this and the negatives accordingly. So, thus we say there is a unique homomorphism. Okay. Next we will see that if we are given two homomorphisms between two groups, then how that can induce a homomorphism from the corresponding group I mean at the level of group rings. So, here we have groups G group, and let us take R and R prime rings. If you wish, you can take them to be commutative. Now, recall that RG is nothing but the sum of all such things AG, G, such that. So, formally these are all the functions from G to R that vanishes outside some finite subset. So, we put in this handy notation, we put this in this way that AG equal to 0 for all but finitely many G's. Okay. Yeah. So, as I was talking about, suppose we are given okay. So, here maybe okay fine, I think ring, I have one ring and two groups ring, and suppose I have two groups G and H. So, now let phi be a homomorphism from G to H homomorphism, then we take a typical element from this RG, namely this, where as I said that AG vanishes for all but finitely many G's, and we send it to. So, we do have a natural thing that AG times phi G, G in G. Okay. So, this is my starting with the typical element, I send it to here. Now, it is quite easy to see that in this way we are actually defining this whatever we have defined here is a homomorphism between from RG to RH. Okay. So, thus a map group homomorphism now extends at the level of group rings. Okay. So, the next example is very important, which we call substitution principle, or sometimes some authors also call it evaluation homomorphisms. So, like let me so this is about polynomial rings. So, for the sake of simplicity, to begin with, let me first talk about polynomial rings with one variable, then we can similar, we can immediately develop formulate the principle for rings with several variables. So, here let us first consider a ring R. So, you may assume it commutative if you wish, and we consider the polynomial ring in one variable. Okay. So, and suppose we are given a homomorphism phi, a homomorphism from R to R prime, where R prime is also a ring. Okay. Suppose we are given a ring R prime and we are given a homomorphism from R to R prime, then and let alpha be in R prime. Okay. So, what we are going to do is something similar to this, not exactly similar. So, from Rx to R, from Rx to R prime, let us consider this map. So, we take a polynomial. So, a polynomial here looks like this, a polynomial here looks like this, ak x to the power k. We where each ai is in R, let me send that to this element ak alpha to the power k. Okay. So, here the understanding is ak's are 0 for all but finitely many non-negative integers k. Okay. So, if we send like this, then it is immediate that it preserves the additions, right, because addition is happening coefficient wise. Okay. So, once it goes here, so we can immediately see that if two polynomials akx summation akx and summation bkxk are given, then here we take their sum. So, here each coefficient will be ak plus bk, that is same as once we come here we see that the what is attached with alpha to the power k is ak plus bk. So, this preserves addition, and also for multiplication, though for multiplication of the formula for the multiplication of polynomial is slightly complicated, but however the way it is defined. So, we first multiply the powers of x and then together with we multiply their coefficients and then take the sum. Okay. So, the way the multiplication is defined, from that it is immediate that this map is also going to be a homomorphism. This may all go homomorphism from Rx to R prime. Okay. So, thus what we have obtained is the following. What we have obtained is the following, that so from R to R prime we have a homomorphism, namely phi, and from R to Rx we do have a natural inclusion where each group element A is now being viewed as the constant polynomial A. Okay. And we do let me denote this by phi alpha. So, here we have phi alpha, and it is easy to see that this diagram commutes because each A is being sent here. So I think I made a small mistake here. Sorry, phi a alpha to the power k. Yeah, otherwise it won't even make sense. And since phi is a ring homomorphism, it preserves both addition and multiplication. You can from these two properties you can immediately check that this is also a ring homomorphism. So, thus you see that this makes this diagram commutative because each A, if you take an arbitrary A from here, it is sending it to phi A. Now, A is being sent here to the corresponding constant polynomial, and this phi alpha of this constant polynomial is again phi of A. Okay. So, this is so given phi and alpha, we do have a map that commutes, that makes this diagram commutative. Furthermore, this phi alpha is unique. So, let me again explain what it means. So, suppose we want to look for some homomorphism here that makes this diagram commutative. Suppose this is what we are looking for, then what should happen? So, for example, suppose f is a homomorphism that makes this diagram commutative. then f of any typical polynomial so since f is assumed to be a homomorphism, so this certainly nothing but f a k f x to the power k, k less or equal to 0. Okay. So, do not worry, since a k is 0 for all but finitely many case, similarly f of a k is also going to be 0 for all but finitely many case. So, therefore, this is actually going to be a finite sum. Now, okay, I just forgot to say one thing. So, earlier the phi alpha had the property that which makes this diagram commutative and also sending each x to alpha. Okay. So, this is an important property. So, let me again remind you that given phi and alpha, phi alpha is the homomorphism defined like this, it has the property that it makes this diagram commutative sending x to alpha. So, now suppose f is also such a map that f is a homomorphism that commutes this that makes this diagram commutative and sends x to alpha, then we must have alpha to the power k. Okay. We must have this, and as I said that f commutes this diagram, from that it becomes quite clear that for f of alpha k is nothing but, remember here each a is being viewed as the constant polynomial a. So, here f of a k is basically the image of the constant polynomial a k under f, and since we insist that f should commute this diagram. So, f of that constant polynomial should be its image under phi. So, therefore, phi a k alpha to the power k. So, you see that that shows that if f is a homomorphism that makes this diagram commutative and also sends each x to alpha, then f must be the phi alpha, right, because this is exactly how phi alpha of this polynomial is defined. Okay. So, thus it justifies the word that f phi alpha is unique. So, this homomorphism is called the substitution at alpha or evaluation at alpha. Let me again tell you what it is. It is just the unique homomorphism, ring homomorphism that makes this diagram commutative, the unique ring homomorphism, diagram commutative and sending each x to alpha. Okay. Good. So, we have actually seen such things. If you remember that if V is a vector space, and T is a linear map from V to V, T is a linear map from V to V, then we do have the following thing. Suppose F is my field. So, F is so this is, I would say, end V. What is end V? Nothing but LVV. So, we do have a homomorphism sending each alpha to alpha times identity. This is of course a ring homomorphism. Now, there is a unique homomorphism that sends each fx to corresponding. So, what is this map to be in simple terms? In simple terms, this is just we apply the given phi on the coefficients and replace and substitute x by alpha. So, similarly, this is what we obtain here, that is corresponding to every polynomial we look at the corresponding endomorphism, which is obtained by substituting the variable by the endomorph by t. Okay. So, this is what we have. So, this is a particular case of this substitution principle that we have seen earlier. Another particular instance of this is the following, which is called the reduction modulo P. Well, what I say that simply like reduction modulo P, where P is a prime. Of course, here I mean in order to talk about the reduction, it is not necessary that P has to be prime, but however prime P's are we consider P to be prime because when P is prime, then we by reducing a polynomial modulo P, we get quite useful information. So let me directly say do that. So so here let me first suppose we are z modulo P z, okay, where let us take P is a prime, though that is not actually necessary. So this is the canonical projection map, okay. Now that immediately okay, and of course we do have, okay. So this is just the usual inclusion. So therefore this is what we have. So what is this map? Every integer we reduce, we look at its corresponding equivalence modulo class in P, and that is viewed as a constant polynomial over this field. Now this substitution principle shows that so see that in this ring we do have a homomorphism, and we have X here which is an element of this ring. So the substitution principle says that there is a unique group homomorphism from Zx to this ring sending X to X itself, okay. So there is a unique group homomorphism sending the variable to the variable itself, okay. So how is that defined? Suppose a0 up to ak xk is my polynomial. What is going to be the image? So basically what we are going to see is we will take each and every coefficient modulo p. So that is exactly going to be my image, right. So this is called the residue of the polynomial modulo p, okay. In fact, you see that this can be further generalized, what we have actually done here. So suppose we are given also a very obvious observation. Suppose we are given a ring homomorphism, ring homomorphism, then we can further extend this ring homomorphism between the polynomial rings as well. So how to do that? So basically we will consider r prime to be included inside r prime x, right. Then so this is simply the usual inclusion. Then there is a unique homomorphism which is exactly defined like this. Okay, that makes this diagram commutative. So any ring homomorphism between the rings can now be extended to homomorphism between the polynomial at the level of polynomial rings. Okay. So these are kind of the linear, the one with linear endomorphism and reduction modulo. These are some of the common instances of the substitution principle. Of course, as I said, that this is perhaps the most important ring homomorphism that we encounter in whichever area of mathematics we deal with, because we do arrive at polynomials, and then we have to evaluate polynomials at certain points. So that evaluation is possible by the virtue of this ring homomorphism, okay. This is not the symbolically we are doing something, this is something very concrete. So that is what we have discussed here, and this can be even further generalized to polynomial rings with several variables. So let me say that to you. The verification is also quite common, and for several variables the formulation of these results I will be mostly leaving to you. So as usual I will have two rings x1 up to xn, I will have two rings x1 up to R and R prime, and we do have a homomorphism from R to R prime, assume that, and also alpha 1 up to alpha n, let this be belongs to R prime. So, given all these, we will now show that there is a homomorphism, unique homomorphism. Uniqueness I will be explaining in which sense in a moment. So, there is an homomorphism from this polynomial ring to R prime, sending each xi, so extending the previous one, extending the given one, and sending each xi to alpha I. So, how is that defined? Recall that here a typical term looks like this. Okay. So, all but finite limiting coefficients are 0. Very naturally, these are being sent to and then alpha 1 to the power I1, alpha n to the power I n. Okay. Since phi is a homomorphism, you can immediately check this is also a ring homomorphism, right. So, so given any homomorphism from R to R prime and any pair, so given any phi and any pair, we get a corresponding homomorphism. And in case of several variables, the diagram would be the following. So, like here also you have to replace this by appropriate things, and then you can immediately see that this is going to be the unique ring homomorphism, making this diagram commutative and sending each xi to alpha I. Okay. Sending each xi to alpha I. So, that is how the substitution principle in generality looks like, and an interesting application of this a routine or a common application of this substitution principle in the generality is the identification of the polynomial ring. So, in a sense some separation of variables you may say, but again the word separation is to be taken with proper caution. So, all right. So, okay, before that I think also you will agree with me that in the earlier way, the way we show that any homomorphism can now be extended at the level of polynomial rings, that can also happen here. So, suppose R and R prime we have phi, then as usual, so this is just an observation, y1 up to in, let this be a new set of variables. So, as expected that this is the usual inclusion map, that is every element is being viewed as a constant polynomial, and therefore, by this substitution principle we do have a unique ring homomorphism, making this diagram commutative and furthermore sending each xi to alpha yi. Okay. This is just an immediate corollary of that. Okay. Now, come to the thing which I was saying a few minutes before, that is identification of the polynomial ring. So, suppose we are given variables x1 up to xn and y1 up to yn, or in fact this is what we can do. Then we do have such things. So, x1 up to xn, we do have two rings y1 up to yn, okay. And at the same time we first talk about this ring, this is a ring, right, and so let me call this ring for the time being P, and then we talk about P of y1 up to yn, that also we are allowed to talk about, right. So, thus this is basically okay. So, So, loosely speaking, first I take the bigger polynomial ring with all the n plus m variables, and in the second on the other hand, first I have constructed a polynomial ring in the n variables, I have adjoined n variables, then whatever we obtain with that I adjoin m more variables. So, our intuition says that like we should get the things same. So, that is exactly the point. We are going to show that these two rings are isomorphic. So, how to show that? Again the substitution principle. The same substitution principle. So, so this holds for any n, right? So, therefore, the way we attack is the following, very simple. From R to, of course, P, we have the natural inclusion, right, from R to P, and then from that we come to what we have just decided. Okay, yeah. So, we simply come to y1 up to ym. Okay. Yeah. So, what is this map? So, each small r is now being viewed as a constant polynomial in the variables x1 up to xn, and now that is being therefore, it is lying in this ring, and then is further viewed as a constant polynomial over in this ring, where in this ring with ring over this and with the variables y1 up to im. Okay. So, that is this homomorphism part is clear. Now, what we do is very simple, that in this ring, so we do have a homomorphism, a very natural choice, and then at the same time we have that in this ring we have y1 up to im, and also we do have, since we have p, we have these elements also lying inside the same ring, right. So, all these elements lie in this ring, this is same as this. Now, by substitution principle we can immediately talk about a ring, we can immediately talk about the substitution homomorphism that sends each xi to xi and yi to yi as well. Okay. Do not confuse that this is not the usual identity map, because rings are different. So, thus we obtain a homomorphism from here to here, okay, from this ring to that ring. Now, there are multiple ways to show that this is a isomorphism. Maybe the best idea to learn, best idea to practice practice applying this homomorphism, applying this substitution principle is to find the reverse map using this principle. So, that thus now you have the situation that R upon x1 up to xn you do have here, which is naturally included inside xn. Okay. The map is very natural, and then you use further substitution principle to get the reverse map from here to here. The final detailed verifications I am leaving that to you. So, just by repeated use of substitution maps, substitution principle, we see that these two rings are isomorphic. So, in the very special case when we are just having only two variables x and y, so what this says is R of x y. So, the polynomial ring in two variables, that is exactly same as first we consider this ring, and then we consider first we take this one variable polynomial ring, and with that we will take another further one variable polynomial ring. And what is this isomorphism? So, like if we specialize this to this situation, for simplicity, we see that given any polynomial, let me show you by an example, x cubed y to the y square plus x5 y to the power 4 plus 3y square plus 2yx plus 1. So, where does it being sent? So, here it is simply being sent to. So, how do we visual, how do we see it here? So, okay, let me introduce some more terms that will understand then what I am talking about. Then let me again add some x cube y to the power 4. Let us say x cube y to the power 4, and let us say here 2x to the power 7 y. Okay. If this is my polynomial, where is being sent to? So, basically we have to view it as a polynomial in the variable with coefficient from which coefficients are also polynomial in x. So, the way we should organize that, okay, so since x to the power 5 plus x cube y to the power 4, then we have x cube y square. So, remember now this is the ring coefficient ring, and then you understand that 2y plus 2x to the power 7 y plus 1. Okay. So, the starting with a polynomial in two variables, what we will do is corresponding to, so the terms having the same power of y, we just add their coefficients. So, here the coefficients are polynomial in x. So, thus we will arrange the polynomial in this way. Then we will once we arrange the terms in this way, that the coefficients of the same power of y are being added up, then that is exactly going to show me how to view it as a polynomial with coefficients from Rx in the variable y. Okay, the most obvious one. All right. So, this is about the substitution principle for polynomials. So, as I said, this is perhaps the most important ring homomorphism that we are going to deal very often deal with in whatever branch of mathematics we study. Okay. Now, let me talk about the relation between let me get into the relation between ideals and ring homomorphisms. So, before that, of course, I should give another example of a ring homomorphism. So, let R be a ring and then I be an ideal. So, I do not bother about whether left or right it is. So, as I said that unless otherwise stated, we always we develop the theory for left ideals for most of this course, and like the analogous results we can formulate and prove for right ideals as well. And if in many cases the ideal will be both sided ideal, so you do not have to do anything else, and when the ring is commutative, then again you are in the you do not have to do anything. So, when the ring is commutative, then already you are done. Anyway, so this is called the canonical homomorphism. Like you can see that this is analogous to the quotient linear transformation for vector spaces or quotient homomorphism for groups. So, before that, let me tell you how this is defined. So, here a plus I and b plus I naturally defined as a plus b plus I. Similarly, for the multiplication, okay, it is easy to see that these are well defined, because if a plus I is a prime plus I, that means a minus a prime is in I. Similarly, we will have b minus b prime is in I, then a minus a prime plus b minus b prime, which is a plus b minus a prime plus b prime is also in I. So, it is easy to see that this is well defined. Okay. And once this is well defined, we can immediately check that, it is immediate that R modulo I with respect to these two operations, that forms a ring. This is called the quotient of R by the ideal I. So, so here I just want to make one point, that unlike groups, in case of groups we cannot just take the quotient with respect to any subgroup, right? We have to consider normal subgroups, but certainly here we do not have to, we do not have any problem like that. We can take the quotient with respect to any ideal. Okay. So, for every ideal we do have a natural quotient ring, and then we have the canonical projection map which sends each x to x plus I. In view of these two properties, it is quite clear that this is ring homomorphism. Okay. So, now let me connect ideals and ring homomorphisms. So, given a ring homomorphism R to R prime, we defined its kernel to be, this expected, because ring homomorphism is actually a first of all, it is a homomorphism between the additive groups. So, here the kernel means you can consider the kernel of the homomorphism between the additive groups, or for the description this is simply 0. Okay. Of course, then you can immediately check, given any ring homomorphism, kernel is an ideal of R. That is a very simple. For example, you have to just check the product thing. So, if x is in R and if x is in the kernel and A is in R, then phi of Ax is simply phi of A times phi of x, which is 0. Okay. So, this is an ideal. So, given any ring homomorphism, its kernel is going to be an ideal. Conversely, given any ideal, there is going to be a ring homomorphism whose kernel is the given ideal. What is that homomorphism? Namely, this canonical exactly this canonical homomorphism from So, what is such a homomorphism? An example is this canonical homomorphism for the corresponding to the given ideal I, because what is the kernel here? So, simply those x such that x plus I is I, that is x in I. Okay. So, here you see that it is exactly similar to what you have done for group, you have done in group theory. Okay. So, they are also given any normal subgroup, what was the homomorphism, namely the quotient homomorphism. Okay. So now let me talk about the correspondence theorem. So, the theory for ring homomorphisms is quite similar to, in fact almost similar to that of that of homomorphisms between groups, right. For example, the results that we prove for homomorphism of groups, namely let us say the correspondence theorem or the isomorphism theorems, with no difficulty we can develop all of them here. So, so therefore, since things are almost automatic, so I will briefly tell you those theorems. So, and of course, the details like the proofs are almost same as those of in group theory. So, the detailed verifications will be left to you. So, how to, okay, so let me directly write down correspondence theorem. How to prove so what does the theorem say? Suppose from R to R prime you have a ring homomorphism. Okay. So, the first observation is then of course phi r is a subring. That is immediate. The second thing is now the main point, that the exchange of ideals. So, if I is an ideal of phi r, then phi inverse I is an ideal of R. Furthermore, and in fact, it contains kernel phi. Okay. The verification is as usual, I am leaving to you. So, remember the thing is here it has to be the ideal of phi r. For example, if you want to quickly see, so suppose x lies in here, then suppose x lies phi x is in ideal, then for any a phi x will be in the ideal. Okay. So, that shows that ax will be in phi inverse I. So, it is quite immediate. So, the third thing is any ideal here, the image is going to be another ideal of okay, let me put it, I is an ideal of R, implies phi R is going to be an ideal of the subring phi R is an ideal of phi is an ideal of phi R is an ideal of phi I is an ideal of phi R. Next, okay, phi ideal from here goes to ideal there, all right. So, and another thing is I is less or equal to j for two ideals implies, this is obvious, phi I is less or equal to phi j, that is this phi in fact preserves the increasing chain of ideals. Okay. Now, the most important part is, in one hand you have ideals of R containing kernel phi. On the other hand, we have ideals of the subring. And we do have a natural bijective correspondence. How is that? That is actually quite obvious. So, sending each I here, we will simply send that to phi of I. Okay. And since and the reverse map is going to be sending each I to phi inverse I, like that of correspondence theorem in group theory. You can immediately check these two maps are inverse to each other. Okay. Once the correspondence theorem is done, I will talk about the isomorphism theorems. So, broadly it is called the mapping property. Okay, so maybe here let me give an exercise based on this correspondence theorem. So, suppose we are given a ring homomorphism from R to S, ring homomorphism, and let I be an ideal of R, and J ideal of S. Assume further suppose all these are given to us, then okay, so I think I should first talk about the mapping property, then it will be easier. So basically I want to talk about, okay, let me do it here as well. I want to talk about a map from the corresponding quotient rings. How is that map defined? Sending each a plus I to fa plus j. Immediately you can verify that this map is well defined, because if a plus I is a prime plus I, therefore a minus a prime lies in I. So once you apply f, from this property it ensures that fa minus fa prime will be in j, thus fa plus j will be fa prime plus j. So this is going to be an immediately considers homomorphy, this map is well defined, and this is in fact a homomorphism. Okay. This is a homomorphism, and the question is when this is okay. So I think it is better that for a while let me postpone this. I think the mapping property would be much, I mean we will need it here. I mean alone like substitution property, of course it is an exercise of substitution, but it will be easier once we do the mapping property of quotient rings. So property of quotient rings. Okay. What is it called? So suppose we are given two rings R and R prime and a homomorphism from R to R prime, homomorphism, ring homomorphism, and let so all these are given. Let an ideal contained inside kernel phi, okay. Then there exists unique ring homomorphism phi bar, that makes this diagram commutative. Let me put it in terms of diagrams. R modulo I to, yeah, there is this unique phi bar. So this is just the quotient map and this is phi. Okay. So there is a unique homomorphism making this diagram commutative. What is that homomorphism? So if I start with some a here, a by phi it goes to phi a. So a comes here, a plus I. So in order to have the diagram commutative, a plus I must be sent to phi a plus I. So this is the homomorphism. I mean this has to be the homomorphism. Okay. Now it is easy to check that this homomorphism is yeah, so easy to check that this is first of all well defined, and it's from since yeah, and since this is a homomorphism, we can immediately check that this phi bar is also an homomorphism. Okay. Now the question is, when is this phi bar going to be 1 1? So the phi bar is going to be 1 1. So what is the, so there, what's the if let us say this lies in the kernel, then that means phi a has to be inside I. Okay. So therefore, okay, I should remove that. Okay, maybe I can write it here. Furthermore, phi bar is 1 1 if and only if, phi bar is 1 1 if and only if kernel phi is I. kernel is 1 1 if and only if we do not have yes. So, I have to make sure that nothing nothing non-zero goes there. So, okay. So, yeah. So, it is exactly same as that you have seen for group theory. So, kernel phi is exactly I, and once and in this very special case what we get is called the first isomorphism theorem for ring theory, right. That is R modulo kernel phi is being isomorphic to the image of phi. Okay. So, like this in particular implies group the isomorphism theorem, and of course, we do have the other isomorphism theorems as well. So, okay, so maybe this board I will just use it to complete to state this exercise. So, here I will finish the other isomorphism theorems. So, as I said that this is the a particular situation of this is the first isomorphism theorem. Then we do have the second and third isomorphism theorems, which looks exactly similar. So, like if I and j are ideals, so then we must have okay. So, the I plus j. Okay. First, let me talk about that. It will be really easier. So, let I and j be ideals. Let these be ideals of R such that I is also further contained inside j. Then we must have, so R modulo j. So, try to see in view of this. So, R modulo j is a ring. Okay. So, what is the image of the ideal I under this homomorphism? It is exactly I modulo j, right. So, therefore, and this is a onto map. So, therefore, I modulo j is an, so I modulo j is an ideal of R modulo j, is an ideal of R modulo j of R modulo j, and the most we do have R modulo I. So, what is this map? This map is quite easy to see. This map is quite easy to see that so the most obvious choice. So, take an element here, let us say R plus j, we send this to R plus I. Okay. So, this is the version of the something called third isomorphism theorem, and it is very natural to ask what happens to the second isomorphism theorem. In case of group theory, it was like H, N, like H, K, all these, right. But at that time H times K become, if they are normal, that becomes a subgroup here. But you see here I plus j cannot be a subring. I plus j is an ideal. If it is subring, that means it is whole. So, so therefore, right now, I mean, if we just simply say like this, that actually does not make sense, because this homomorphism is not a ring homomorphism, because these are not even rings. Okay. But of course, we will come to that. In fact, once we get into module, if time permits, then we see that yes, these are isomorphic, but as R modules. So, here we do have module isomorphism, not the usual, not the ring isomorphisms. Okay. So, deliberately I skip this. Now, come to here. So, you see here you can this condition guarantees that for this homomorphy for the okay. So, what is the situation from R to S we have, and then from S to J. Okay. So, this condition f a is contained inside J. So, that ensures, so if we call this map as phi, this is f. If so, what is phi? Phi of R is f r plus J. So, this condition ensures that I is contained inside the kernel of phi. So, let me simply check that if A is in I, then f of A belongs to J. So, f A plus J is 0. So, this exactly phi of A is 0. So, I is contained in the kernel of phi. So, therefore, this homomorphism is nothing but the unique homomorphism obtained in this manner, and the exercise is about when this is isomorphism, so then and okay, so maybe and I am letting it here as well, and this let me call this f bar. F bar is an isomorphism. F bar is an isomorphism if and only if two things happens. First of all, imaginary part f plus j is S, and f inverse j belongs to, is just contained inside I. Okay. In particular, so this is the exercise you can immediately do. Yeah, you can immediately do. This is an exercise of this mapping properties, not exactly of the correspondence theorem, it seems. Anyway, so then in particular, so okay, let me leave it as a question that if f of I is j, and kernel of f is contained inside I, then f bar is an isomorphism. Okay. So, that shows that when we are given isomorphism and we do have ideals on both the sides, then when that descends this homomorphism descends a map from at the level of the quotient rings, and when that map is going to be isomorphism. So, this is a general so just a corollary of this mapping property. Okay. So, now I think I should move on. Okay. So, let me now talk about Chinese remainder theorem. So, the Chinese remainder theorem, I am sure that you have seen in number theory. So, Chinese remainder theorem in elementary number theory or in any first course in group theory. We are going to prove Chinese remainder theorem in the setup of general rings. In fact, we will see that most of the things that we have done for Z, we can generalize that for good enough rings. So, okay. So, let me talk about that. I am not sure whether today I will be able to prove it or not. Chinese remainder theorem. So, here let us assume R is a ring. In fact, we assume commutative. Okay, we assume commutative. So, let me make a definition here. So, suppose we are given two ideals in R, we say they are co-prime. Okay, before giving the definition, let me give you the motivation. So take R to be Z and two integers m and n. Okay. Recall that if m and n are co-prime, if and only if the ideal generated by they have this property, right. This is the property that they are going to have, because one can be written as a linear integral combination of m and n, right. So this is what so this is a co-prime if and only if we are having this. So this I mean in for an arbitrary commutative ring, we do not have the we do not have the notion of GCD or anything, like so far we do not have. Of course, we will be defining that for good enough rings, but like the coprimality, we can you can define coprimality from this using this property. So coprimality from this, so this exactly is defined are coprime if I plus j, this is whole of R. Okay. So thus you can what are examples? When R is Z, then m and n are co-prime. So two ideals mz and nz are co-prime. If and only if they are they are co-prime in the previous sense. Okay. Further examples, take let us say R equal to Z root D. So here the ideal let this be an ideal, another ideal is k plus root D, where GCD of k and D is 1, then they are co-prime. You can immediately verify this. Also in the third example is let us say in Zi, you can take 1 minus I and 1 plus I. So there are many such examples. So the thing is, the notion of coprimality that we had for integers only, now the notion is being extended to any general ring. So any general ring, but here the only thing is instead of looking at the particular elements, we are rather concerned at the level of ideals, because we will very soon see that like working with ideals in general ring, working with ideals is the that is the correct choice, and as a special case we obtain all the known previous results in number theory. Okay. So that is how coprimality is defined. Now let me talk about the Chinese remainder theorem. With that, I will just state. So right now let me just state it for only two ideals, but we will in the next class we will talk about Chinese remainder theorem for more in any general finite class of ideals with which are pairwise coprime. So suppose I and j are coprime, then consider the homomorphism R cross j. What is that map? Sending each a to a plus I to a plus j. Okay. It is easy to see that this map is a homomorphism, right, because component wise we have things properly. And what is the kernel of this homomorphism? It is easily seen to be intersection. So this is a homomorphism with kernel I intersection j. What about the surjectivity. If there just would be one factor, then the surjectivity would be obvious, but now we have actually two factors. So, what about surjectivity? That is exactly is being answered by Chinese remainder theorem. Okay. So, we will be proving this for and okay. So, having assumed this is surjective, suppose that we are able to prove this is surjective, then as a consequence we obtain R modulo R okay. So, like proving it for only two ideals is easier, but as I said, the next lecture we will be proving for many more for any general finite collection of ideals. And one more thing I should just say, and with that I will finish, that what is this? If I and j are, so I and j are co-prime, is an observation, co-prime. So, I j, their product is always a contained inside the ideal, but here we do have something if they are co-prime. That is exactly that is quite easy to see, because one side containment is there, another side containment is if, like, since I plus j is R, so there exists A in I and B plus in j, so this is 1, so AC plus BC is going to be C. So, this side is easily seen to be inside Ij. Okay. So, when they are co-prime, then this is in fact R modulo Ij. So, this is the simpler version of this is the special case of Chinese remainder theorem. In the next lecture we will be proving the general version. Okay. So, with that I will finish.